So thank you very much, and let me continue where Marco ended. So first of all, thank you for Hans and Marco for the introduction. Thank you for COGEN Europe for commissioning the study with us, and also thank you for inviting us to present the study today. I will give you 20 minutes, 25 minutes intro to some key results of the study, and I will start with a bit of a scene setter. Yes, perfect. With setting the scene, basically, what is the background of the study? Oh, I need to click myself, sorry. So I will cover first a bit of a background to the study, like the introduction was the background, and then go into some of the key results, not covering everything that is in the study. As already outlined, the study will be published. It has a relatively comprehensive modeling appendix with like a lot of results, which is impossible to present during a meeting like this. So we'll focus on some key results today. In terms of background to the study, we were asked to analyze basically what is the role of cogeneration within the evolving European energy system in the framework with the targets that were already outlined by the previous speakers, like the ongoing idea to reduce emissions going forward with a framework condition that's increasingly shaped by the question of affordability and competitiveness. Also the ongoing, not yet completed transition of the energy system as a whole within these framework conditions, industrial end users and district heating operators need to continue doing their business. And the question here is for them, of course, how to do this in a competitive and affordable way. And therefore the question is, what is the role of cogeneration here? To provide efficient decarbonization, cost-efficient decarbonization, and what can be a wider system impact. And that's something that we have covered in the study by an approach that was specified by COGEN to look into very specific, very detailed case studies comparing applications of cogeneration technology with alternative setups. And what we've done here is define, together with COGEN, 5 use cases of cogeneration technologies and specify what is called hybridized setups. Hybridized setups means that's not only just one technology, and that's something that Marco highlighted already in his introduction statement. It's not just one technology, but it's a bundle of technologies that are used by the end users or by the district heating operators. So in the hybrid setups that include CHP technologies, we have like the CHP together with like electrified technologies, together with like backup boilers, together with like storage is very important to provide some flexibility. And we compare in those use cases these setups against like, again, hybridized setups that do not include a CHP technology. So where we basically need to meet the same demands, electricity demand, heat demand, steam demand, in one case cooling demand, by a setup of technologies that do not have a CHP available, so therefore need a different setup of technology. So this could be gas boilers that gradually use green gas, power to heat technologies being either direct electric boilers or heat pumps, and again, of course, heat storages to provide flexibility. And so we have defined, and I will go a bit into the definition of those use cases later on. We have defined like hybridized CHP setups and hybridized non-CHP setups and compare those two. And how do we compare them? So we have basically specified 5 dimensions that are interesting for this comparison. We've looked into showcasing how there's like complementarity between the usage of these technologies with like the electrification and renewable technologies. We've looked into the use of fuel and energy efficiency questions. We've looked into how these setups contribute to the decarbonization target. We've looked into how these setups contribute to the question of competitiveness and affordability. And finally, we've looked into the wider system impact, to what extent the setups can contribute to providing system services that are increasingly needed in a decarbonized electricity system. I'm not going into full detail of this, maybe just to highlight a few things on the modeling approach. So what we have done, we have specified together with COGEN those 5 setups in the non-CHP and CHP configuration. We've looked into like two dimensions. The one on a long-term basis, on a structural basis, what is like an efficient and cost-minimizing structural setup of these bundles of technologies. So how to size them, how to combine them, and how to integrate them together in like a portfolio of technologies, and then on a short-term basis, basically to dispatch them in a way that considers all the operational restrictions and conditions and framework conditions that are around, and get like a cost minimal production of cost minimal meeting of demands of the end users of the district heating systems. And that was to some extent an iterative process. So when you dispatch those installations, you find out that there's like probably a more optimal way of sizing them. And at the end, we came up with like setups that were like leading to low total cost while being dispatched in a cost optimal way over the course of a year. So we did like a yearly modeling for each hour of the year, but we also modeled like the full horizon until 2040. So it's not just a perspective of looking into what is happening today, but also looking ahead what is happening in 2040 with like a transitioning energy system that changes, of course. We have like in all countries an increased deployment of renewables. We have in all countries changes in the generation of those technologies and leading to different prices over time. So the structure of the electricity prices is evolving over time, and that's something that's considered here. And we've also considered scenarios for energy price and also gas price and carbon price that is basically impacting these this modeling. So it's not a static modeling, but it's like a relatively fine, granular, hourly modeling up until 2014. We have done this for 5 use cases, and all these use cases are in different European countries. So we've looked into an industrial application in Spain. We've looked in another industrial application in Italy. We've looked in 2 district heating systems, one in Poland, one in Romania, and we've looked into a pulp and paper use case in Germany. By choosing those use cases, we have on the one hand covered both dimensions, the question of how can CHP contribute to district heating and how can CHP contribute to industrial energy use. And we have also covered like the different and diverse status of energy systems that we have in Europe at the moment. So we have like very renewable heavy energy systems like the Spanish one, and we have on the other hand like systems that are still have a large part of the transition ahead of them when looking, for example, into the Polish or the Romanian system. And we also have looked into the usage of different CHP technologies here. So you see indicated here some of those cases are using gas turbines, some of these use cases use gas engines, and therefore we have like a broad variety of different applications in different framework conditions of CHP. There's maybe one thing important to mention. We've spoken about, all speakers before me and also myself, about hybrids and hybridification of CHP, and that's something that's being done by complementing CHPs with electrified technologies. And in all the cases, we do have very significant electrified generation technologies in these portfolios. And in most of the cases, not in all of the cases, these electrified technologies are capable of meeting the full heat demand. So that means we enable in these setups the generation of most or all the heat that the end user or the district heating system needs to produce also without CHP, and in case of industrials, in Spain and Italy, completely with electrified technologies. Just by hybridizing it, there's not the need to do it all the time, and that like generates the flexibility that allows to actually react dynamically on an evolving market where we see, and that's something we will be seeing. We can react to the changes in the market environment, to the power prices dynamically by either using the CHP or using the electrified technology, or in case of district heating systems, of course, using other components of the district heating generation. We do have evaluated the use cases across those 5 dimensions that I mentioned before. Those are all covered in the full study. We will not, or I will not cover all the dimensions today. So we made a selection that's like amenable to the time frame that's provided, and those are highlighted here, and I will not go through them here on this overview, just to show you. We have like a sub-selection where we cover like how CHP complements renewable generation. We will look into the energy efficiency. Again, we do not cover all the use cases, but it's a selection. The results of the other use cases are then covered in the full study. We do cover some aspects of decarbonization, so industrial decarbonization, impact on the emissions, but also the efficient district heating criteria, looking into the industrial competitiveness cost, and we will leave out ancillary services because that's a really big and broad and endless topic to cover. So that's something we're going to spare you for today. So, going into case study insights. As mentioned before, we picked some aspects and we also picked some use cases. So top right, you usually see the logo and the flag of the use case that we picked. We tried to select all countries and use cases for illustrating some of the aspects. Here we're looking into Spain, and we look into the ability of CHPs to react on short-term price signals to provide like short-run flexibility. And that's something that's very nicely illustrated here by looking into what's happening in the Spanish market, where we have like, in this case, 2035, so already looking quite some time in the future. We have like quite a volatile power market. This is like the red line that's basically jumping around, that has like some peaks, but that also still has some zero hours where like electricity is like either wholesale electricity either for free or might even turn negative. And then we see how the portfolio of technologies that we have set up here can react to those price signals. And what we see here is like a relatively easy to understand fact. Whenever the power price is high, it makes sense to use the CHP to produce large parts of the steam and heat demand. That's like the bottom graph, where this purple CHP throughout the stack is always purple. So the purple generation block is relatively high when the price is relatively high, and whenever there's like cheap electricity available during noon, when there's like a lot of solar generation in the Spanish system, then the electric boiler jumps in, and we have also included in the setup heat storage, and this heat storage can also store some of the excess generation during cheap hours and put it like in the future. And that's like something illustrating the ability of such hybrids to react to power prices, and that's something that will stay important also going forward in time. Oops, wrong direction. So then we look a bit into the long-run dynamics of CHP usage. And what we've done here, we've contrasted 2 points in time. So basically, first thing is we look into 2025, like 1 year past. Like when we did the modeling, it was still a bit prospective. Where we basically have the current price duration curve, where we have a few hours that are low price, zero price. That's where the one is. Then we have a few zero negative priced hours, then a plateau of electricity prices and peak prices, and accordingly we have like the generation of the portfolio of technologies, where we again have like when electricity prices are high, CHP produces; when electricity is cheap, electric boiler jump in and produce the heat. When we move down the line into 2040, we see quite a significant shift in the structure of the electricity prices. So the increased deployment of renewables actually leads to a shift in the price duration curve. Like the curve shifts to the right. We have much more hours of zero negative prices. We have the plateau that's basically significantly reduced, but there's still quite a lot of like actually quite high priced hours when there's no renewable generation and when some other generation needs to kick in. And accordingly, also the generation portfolio shifts its usage, and we have like much more production of heat by the e-boiler, by the electrified technology. We have like much more usage of the storage that can actually take up much of the excess generation. And then still, when prices are high, there is the flexibility of CHP to actually generate the heat and profit from the high electricity prices and avoiding and shielding basically the end users from these high prices. We've then looked also into like long-run dynamics for district heating systems, and there one of the interesting facts, and that's something that we're going to illustrate here on the Romanian use case, where we've modeled the CHP use by a gas engine in Romania. And what we see here is that there's a pretty nice alignment between the seasonal demand for heat and the seasonal demand for electricity that is expressed here by the Romanian power price. So what we see here is the Romanian power price is particularly high in winter times in 2035 again, where we have less renewable generation here and or more demand. And exactly in those times, there's also more demand from for heat, and there's also more runtime for of the CHP. So we have again this purple block of CHP generation that matches quite nicely the structure of the electricity price that see in the top graph in the red line. So high prices of electricity, high heat demand, high CHP generation, and this like electricity generation where there's no immediate use in the district heating system can contribute to meeting electricity demand in winter. Next up, we look into again one of the aspects that we already covered before, the question of how does CHP interact with high electricity prices. And what we've done here is we basically take 2030 as a year. We this time look into the Italian use case. The Italian use case is an industrial end user that uses CHP to produce heat and cold for pharmaceutical industrial player, and we again have a hybridized setup. So we have like the gas engines as the CHPs. We have like electric boilers and electric chillers here, and we look into 2030 this time. Of course, having the same price structure time series. The price is the same in both graphs. However, on the left-hand side, we have the CHP included in our hybrid setup. On the right-hand side, we have no CHP and actually do have a gas boiler that would react to high prices. So we are not forcing the system to actually use electrified heat all the time, but we basically do a least cost dispatch, and the electric boiler is always used when it's like more economically to use it. And if gas is cheaper, then gas is used. And what we see here is on the left-hand side, we have like a lot of like CHP generation, where CHP can produce the heat and also produce the electricity. And on the right-hand side, we see the e-boiler does more or less the same generation as in the left-hand side, but it's in many hours of the year cheaper to produce the heat with the e-boiler, with the gas boiler than with the e-boiler. So bottom line here is when you have like the option to run your CHP or your e-boiler, and you have the option to run your e-boiler and a gas boiler, then the CHP does not really reduce the runtime of electrified heat, but it actually reduces the need to use a gas boiler. Of course, you could do a more cost-intensive dispatch. You can force the e-boiler to produce more heat, but this will only get more expensive. So it's like basically taking into account also the dimension of like affordability and industrial competitiveness. Yes, you can of course force them to produce more heat in an electrified way, but it will not get cheaper. Next up, an issue that we come across in some of the jurisdictions that we looked into. This is the question of grid connection, and we specifically looked into this topic here in Spain, where this is, as just discussed before the presentation here, is a very imminent issue, that getting grid connection capacity is an expensive process and is also a lengthy process. And what we can showcase here is that basically the electrified, the electrification of heat, the electrified hybridization needs like an increase of the grid connection capacity, and that might be something that's very difficult to achieve. It's costly, but it's also like difficult and lengthy to get this grid connection capacity even. And what we can show in the hybridized CHP setup is that basically you can delay this grid connection capacity for some time. You can use the CHP immediately to meet your heat demand. You can put in an a direct electric boiler or electric boiler of any sorts to basically produce heat within the existing grid connection capacity. So you have grid connection capacity, you also have like on-site generation of electricity. You can use those two to produce some heat, and only over time increase the grid connection capacity to achieve what we have called like the full capacity electrification. So basically the ability of the setup to also meet the complete heat demand in an electrified way, just not already in 2025, because this grid connection capacity is hard to get and hard to increase. And therefore we can basically bridge the gap in this use case using CHP over the time when there's like no grid connection capacity expansion possible. Next up, we looked into the question of fuel efficiency, and we here look into the district heating use cases. We've done the same exercise, of course, also for the industrial use cases, but here covering the district heating use cases. So we look into Poland and Romania, and the question that we have asked ourselves is, when comparing the hybridized setup with CHP against the hybridized setup without CHP, what is like the overall fuel usage? And the overall fuel usage is a combination of the fuel that's like used on site. So basically in your CHP on site, or in your gas boiler on site if you use it, and also what's like the upstream usage of fuel, because when you don't have a CHP on site, you need to take grid electricity, and in many of those countries, and those two are a particularly pronounced example here, you have like an electricity generation that's still fossil fuel based to a large extent. So when you use more electricity, the marginal electricity that's used by not having the CHP available is in some hours of the year fossil fuel based. And what we look into here is like when you look on the left columns, the non-CHP columns all the time, they basically answer the question, if you don't have the CHP, if you need to source the electricity from the grid, is this marginally produced by fossil fuels, and if so, from which and to what extent? And when you add this upstream fuel consumption to the consumption on site, you basically see that over a long time, like the hybrids, including a CHP, use less fuels overall than the hybrids that do not have a CHP available, simply because you have like more, or one of the key facts is because you have more need for electricity, and this electricity might be produced or might be required in hours when there's no renewable generation available. And to some extent, the mirror image of this fuel consumption exercise is then the question of looking into the emissions, because of course, when you use like fossil fuels on site, you have like on-site fossil fuel emissions. But when you take off electricity off the grid, that's like produced using fossil fuels, then you have also fossil fuel emissions that are upstream. Plus, you have like grid losses that basically are incurred to produce the to ship the electricity or transport the electricity to the site. And what we see is basically when we make the exercise and again look into if we have the CHP available compared to when we do not have the CHP available, and when we need to meet the electricity demand of the user by off-taking electricity, and also do not have the ability to basically re-inject electricity in the grid when it's excess compared to what the end user needs, then we have like more electricity generation for the grid, centralized from the grid, and in the countries analyzed and the use cases analyzed, that's to some extent, to a decreasing extent, that's of course very clear when we look into the involvement to a decreasing extent, but it's still to some extent produced by fossil fuels, and they produce emissions. Just to flag, that's something I forgot to mention. All the modeling is done using the T1DP 2024 assumptions. So we have used like the basically standard assumptions for the evolvement of the power system. So there's like a very dynamic evolvement of the system over time. So up until 2040, there's a very significant deployment of renewable generation, and that's very visible here, where we see the marginal effect is like decreasing over time. So that's very pronounced at the start, and that's tapering off to some extent, but still, like over the lifetime of the asset park and over the modeling horizon, that's still a positive effect. One of the more tricky regulatory issues is the issue of high efficient district heating, like high efficient cogeneration, and the use in meeting the criteria for efficient district heating. And what we've looked into here is, again, for all the district heating use cases, being the Polish one and the Romanian one, and we highlight here again the Polish use case, how CHP can contribute to achieving the efficient district heating status using this technology shares criteria, and how over time this is possible to meet by including a CHP in the mix. And that's something that was also, and that's important, also considered in the non-CHP hybrids. So we have where we have like a portfolio that does not include CHP. So basically, we also have achieved the efficient district heating criteria in this other setup, in this other hybridization setup. But that of course has some operational impact. So in order to achieve this this efficient district heating criteria, you need to run your assets in a certain way, and that was considered here, and that basically points to the fact that this is like possible to achieve with efficient district heating with a CHP that's included in a district heating system. Sorry. Then we look into the cost competitiveness thing, the dimension of how can CHP contribute to generate heat and energy more broadly in a cost competitive way. And what we've used as a metric here is the levelized cost of energy. So we're basically looking into the question, how much does it cost to supply the energy that's required by the end user or by the district heating system. So we do not, levelized cost is not just electricity, it's like energy here. So that means the electricity that's required by the end user, the heat or steam that's required by the end user, and both put together as the energy delivered, and looking what does it cost to supply this energy over the entire lifetime, over the entire modeling horizon. And basically looking into over the 15 years that we cover in our modeling, how much does it cost to meet all this energy demand, and compare this again in those two hybridized setups, including the CHP and not including the CHP. And what we see that the flexibility that's provided by the CHP to avoid like high electricity prices can help to achieve like cost reductions compared to the electrified setup. And that's like true for all the three industrial setups, and we've seen have similar results also for the district heating case studies that we do not cover here. So, and that's basically the summary of the analysis. So we looked into 5 use cases in 5 different countries using different technologies in different industrial or district heating applications. And what we see is that in these 5 case studies that we analyzed, there's basically a contribution of the CHP usage across all the dimensions that we looked into. So we have like the ability to use like electricity when it's like very expensive. We can avoid the electricity connection queues to get like electrified heat already quite early on the system. We have like the more efficient use of fuels in the fuels, and this can be increasingly also, of course, decarbonized gases by using CHP. We have like the decarbonization benefit that when we include like in a full picture also upstream emissions from electricity generation, then we have like a positive impact on the emissions. We can achieve using CHP the efficient district heating criteria. The levelized cost of energy can be lower than in the electrified hybrids, and the wider system impact. That's something we have not covered in this slide deck, but it's again in the study. What we can show is that what's like factual is that all these CHPs, of course, can produce ancillary services, and those ancillary services can add a revenue stream to those use cases. So these use cases might be even better from selling ancillary services to the system operators. However, an important thing, and that's also highlighted in the study, not all the ancillary services that CHPs and the technologies can provide are actually remunerated at the moment. So there are some services that can be provided that are also required, but that are not leading to a revenue stream, but some do, and those revenue streams would actually improve the use cases in a commercial from a commercial point of view compared to what we see here. I think that's it. Thank you very much.
Thank you again, and thank you to Compass, and thank you for all your hard work and your patience with us, and we're very pleased to have this final output, and we're looking forward to sharing more of the results as they become available in the coming days and weeks.